Brett is coming to us from Mississippi State these days, where he's a postdoc working with our own Angel Tanner. For those of you who remember Angel, she was here for a while. She's now tenured faculty at Mississippi State. Brett's working with her. Before that, Brett went through the Florida Institute of Technology for his undergraduate, then the University of New South Wales in Australia for his PhD, and then he came back to the States and is now over in Starkville. And I cleared with him that it was okay to say we're not going to cry too much if Mississippi State lost for the second time in a row.
Yeah.
But good game in case you didn't see it. One of those stunning buzzer beater kinds of things. But we're not going to talk about basketball today. Instead, I don't know if you read his abstract carefully. It's sort of basketball. The golf ball going in front of that. The basketball's on fire. But I don't know if you read the abstract carefully, but you may learn something today about one of my new favorite terms, secular chaos, which is a good thing. So, Brett.
All right. Thank you, Todd, for the excellent introduction. And yeah, that basketball there is really a hot Jupiter transiting a star. So today I'll be talking about determining the origins of hot Jupiters, because these are planets that are Jupiter mass on orbits that are less than about 10 days, and of course we don't see them in the solar system. So these logos, so as Todd mentioned, I did my PhD at University of New South Wales, and I just accepted a job offer, another postdoc at the University of Southern Queensland, where I will be moving out there in August to do follow-up of transiting planet candidates that will be coming from TESS using the Australia's Minerva telescope array. But today my talk is going to be focused on the hot Jupiters and trying to determine their origin. So let me give you a brief outline of my talk. So first I will sort of set the stage and the motivation for why I'm doing this work, and that's based on understanding the solar system a little bit better, but in particular the hot Jupiters and how you might migrate a planet into a close orbit and how that's associated with planet formation and migration. And then just to give a bit of an overview of two very popular planet detection methods that are also related to my work. So the radial velocity method and the transit method. And in order to measure the obliquities of hot Jupiters, so when I'm talking about obliquities, I mean the angle between the orbital plane of the planet and the star's rotation axis, which I'll show in more detail. So that will be a little bit clearer in a few slides. But in order to do that, you use the radial velocity technique, and you need to have a transiting planet. And then I'll talk about the results that I've obtained during my PhD, as well as the work that I've continued at Mississippi State. And then I'll put that into the context of planet formation and migration. And then I'll talk about future work that needs to be done. Hence, we need more data, of course. And then the conclusions. So I thought I would start off with talking about the solar system, because obviously it's what we know best. And one thing that you'll notice is in the inner part of the solar system, you have what are called terrestrial planets that are small and rocky. And then further out, you have the gas giant planets. And we believe that this is due to the processes behind planet formation. Another thing that you'll notice about the solar system is that all of the planets are along the same plane, so they're all coplanar, and they all orbit in the same direction that our sun rotates in. And that's a little bit clearer right here. So Earth is, if you ignore Pluto, Earth, I think, is the most inclined planet relative to the star's rotation axis, which is about 7 degrees. And as I mentioned, this is likely a result of planet formation. So how do you form planets? So you start off with a large gas cloud. It begins to collapse. Initially, it has some net angular rotation. So as it collapses, it will conserve angular momentum. It will start to rotate faster and collapse down into a disk. And from the disk, you have planets that form. Close to the protostar, the region is fairly hot, so you don't have a lot of icy materials, and it's the icy materials beyond what's called the snow line or ice line that can build large planets that will eventually become gas giants. But inside the ice line, the density of material is much lower, so you form small rocky type planets. And that's basically the architecture of our solar system. So this is the core-accretion model of planet formation, and it more or less fits the solar system quite well. However, it doesn't predict hot Jupiters. So when we first started discovering planets around other stars, astronomers were quite surprised by the discovery of Jupiter-mass planets orbiting on periods of less than 10 days. And specifically, hot Jupiters occupy this region right here. So this is orbital period. Of course, the axes cut off here versus planet mass. So objects around 0.3, 0.5 Jupiter masses and larger, and orbital periods less than 10 days. Now, these are all confirmed planets that have masses measured. So if you look at the radii distribution right here, so that's about planets that are about half a Jupiter radii are also considered hot Jupiters. But what you'll notice is that there's a lot of smaller planets, and that's mainly from the Kepler, thanks to the Kepler Space Telescope, which is easier to detect smaller planets using the transit method, which I'll go over in a little bit. So how might you form a Jupiter-mass planet on a 10-day or less orbit? If the model, the primary model for planet formation doesn't predict such planets, then how do you get them? Well, one way, might be, you just migrate the planet in. And one idea that was proposed early on is the planets migrate through the disk itself. So here's just a simulation where the planet generates spiral density waves due to the interaction within the disk. Angular momentum is transferred from the inner part of the disk to the outer part of the disk, and the planet grows more massive and also starts to migrate inwards until it fully clears out a gap in the disk, and the migration kind of slows down. So in this simulation, the planet migrated from about 1.3 astronomical units to about 0.6 AU. So this migration, there we go, this migration mechanism seems to explain hot Jupiters to some degree. I mean, this is one possible route for producing a hot Jupiter. And in fact, we have seen protoplanetary disks that have sort of these gaps in them that indicate possible active planet formation and maybe even planet migration, though that's debatable. So here's an example of HL Tau that was taken with ELMA. So this would solve the problem of producing hot Jupiters unless their orbits are found to be misaligned, which is actually something that has been recently found. So not only did astronomers start finding planets, large planets on short period orbits, they also started finding planets that have their orbital planes misaligned with the rotation axis of their host star. So how do you measure the alignment of the plane of the planet's orbit and the star's rotation? Well, before I get to that, first I will talk about two widely used techniques to detect planets that are related to measuring the spin-orbit misalignments. So one is the radial velocity method, where you're basically measuring the Doppler wobble of the planet as you have, or Doppler wobble of the star, sorry, as the planet is orbiting the star. And of course, in this case, you don't see a Doppler wobble because the orbit is aligned along the plane of the screen, so you need to have some radial component towards or away from the observer. And what you do is you take time series high-resolution spectra to measure see the shift in the stellar absorption lines. And in fact, this is work that I've done using the Anglo-Australian telescope. So here's an example of some high-resolution spectra. Now, it's hard to see, unfortunately, with this projector. But right here are the absorption lines that were used to determine the radial velocity of the star. And they're fairly faint and fairly wide, and that's because the star rotates fairly quickly, which is something that you need to measure the spin-orbit alignments, which I'll explain in a little bit. And here's an example of a radial velocity curve for detecting planets. And the reason why I'm showing one from Hat South is because I collaborated with the Hat South team to confirm planets that they found that were transiting with radial velocity measurements. And this work was done, or my contribution was making these measurements on the Anglo-Australian telescope. So here's some example of radial velocities from the AAT. And so far, the Hat South team has discovered 44 planets, which is quite good. Now I'll also talk about the transit method, because you need to have a planet transit in order to measure the spin-orbit angle. So when you're measuring a transit, I apologize, the plot here is hard to see, but basically you have a planet that crosses in front of the star. If you're measuring the photometry of the star over a period of time, then you can see a small dip in the amount of light from the star, from the planet crossing its stellar surface. And here's a few examples of some light curves. And this is from the Kepler Space Telescope. And it's pretty remarkable, the level of precision that Kepler has been able to obtain. So here's the transit. Here's the secondary eclipse, where the planet goes behind the star. So you're actually seeing reflected light from the planet. So you can get thermal emissions and other things from this kind of level of photometry. And then the other thing, I should also mention that you can also detect planets smaller than Mercury using really high precision photometry. So this is an example of sub-Mercurian planet, or planet smaller than Mercury, and this is Kepler 37, though of course you do have to be careful of false positives, such as background eclipsing stars. But in general, the transit method is quite remarkable in detecting really small planets. And it's also really remarkable because you can measure what's called the spin-orbit angle using what's called the Roster-McLaughlin effect. So right here I have a star that's colored blue and red, and what that is it represents the blue side represents the side that's rotating towards the observer, so the light is blue shifted. The other side represents the hemisphere that's rotating away from the observer, so the light appears red shifted. Now when there's no object transiting the star, there's zero net radial velocity effect. But if you were to look at the line profile of the star, of course, the faster the star rotates, the broader the absorption line becomes, because you're getting more of the velocity component from faster portions of the star, instead of getting a very narrow absorption line for a slow rotating star. Now, if you have a planet that's transiting, if I can, you have a different situation here. So let me pause it real quick. So with the transiting planet, it will block out part of the light that's either rotating towards the observer or away from the observer. And if that's the case, you get this really neat kind of radial velocity anomaly. So when the planet is over here, you see more light from the red-shifted hemisphere, so you get a net positive velocity, and then when the planet moves to the other side, you get a negative radial velocity. Now, I keep mentioning spin-orbit angle, and what I mean by that, and hopefully this figure will clear it up a little bit, is the alignment between, so here's the orbital plane of the planet, here's the stellar spin axis, so it's the angle between the planetary orbital axis and the stellar spin axis. Now this is pretty complicated, but one thing I want to point out is you're not actually measuring the true spin orbit angle, because unfortunately you don't know the orientation of the spin axis of the host star. So because of that, you're measuring a projected spin orbit angle, and in most cases the angle, the true angle, will be larger than the projected angle that you measure. Now you can disentangle that if you know if you can measure the angle of the stellar rotation axis, maybe through astroseismology, so measuring the pulsations. But for most cases you can't do that, so you get a projected angle. Now the Roster-McLaughlin effect is not something that's new. It's new to exoplanets, but it's actually been measured almost 100 years ago, back in 1924, by Rossiter and McLaughlin. That's why it's called the Roster-McLaughlin effect. And they measured it for eclipsing binary stars. So here's an example for Beta Lyrae, and here's an example of a goal. Now, when you have a planet transiting the star, it also affects the line profile of the star. So there's actually another technique for measuring the spin orbit alignments other than just the Roster-McLaughlin effect. And in this plot here, I show the effect of the transiting planet on the line profile. So you see a little blimp here, a little blimp here. So this represents the velocity component of the absorption line. And then when it moves over here, you see the blimp on that side. And this blimp actually shifts, it's what shifts the radial velocity when you're measuring the velocity of the star. So if you use like a cross-correlation function to determine the radial velocity of the star that you're observing, then this effect will modify that. These figures do not look very good. So if you measure the radial velocities of the star when the planet is transiting, how do you actually measure this? How do you get the spin-orbit angle from that? And you get it from modeling basically the shape of the Roster-McLaughlin effect. So here I have the case of a well-aligned system, and you see this is the characteristic shape for an aligned system. Here we have a significantly misaligned planet, and you have a negative velocity anomaly during the entire transit because it's blocking the redshifted hemisphere. And then here's a case of a retrograde planet. So in fact, we've even discovered planets that are on retrograde orbits. And the amplitude or size of this effect is based on how fast the star is rotating and also the area that the planet is blocking on the surface of the star. And then here's a cool animation that's using the Doppler tomography method. So this is looking at the line profile of the star, and you can actually see basically the shadow of the planet in velocity space on the average or the least squares deconvolution, which basically gives you the overall line profile. So the reason why I mention this method is for stars that rotate really fast, their line profiles become very broad, and it becomes very difficult to measure high precision radial velocities. But with Doppler tomography, you can measure the spin-orbit angle to higher precisions compared to using or doing it with radial velocities. Okay, so now I'll go over the results that I've obtained for measuring stellar obliquities or spin-orbit misalignment. So I started a project called Stellar Obliquities and Planetary Alignments, SOPA, which I've been told in Spanish means soup. So most of the data that I have, or most of the spin-orbit angles that I've measured, have come from high precision, high resolution spectroscopy on the Anglo-Australian telescope. And that's located, it's really hard to see, I apologize, right here. So fairly far inland in Australia. Here's Sydney for reference, Brisbane. And I'll be moving to Toowoomba in a few months to start my new position at USQ. And I think this is probably a better image of a spectra than the previous one that I showed, because you can actually see sort of the, hundreds, if not thousands, of stellar absorption lines that are used to measure the radial velocity of the star. Now the instrument that I used doesn't use just a standard slit that you would normally use for spectroscopy. It uses a fiber bundle, which has a larger collecting area on the sky, and then that is reformatted into a pseudo slit, which is 0.63 arc seconds. So you get high resolution using a small slit, but large collecting area on the sky, so that if you're observing in poor seeing conditions, you're not losing a lot of light. So this is my first result. This is for WASP 79b. And when you look at the radial velocity curve, it has a positive radial velocity during the entire transit event. So that means that this planet is on a polar orbit. So this was a really exciting result, especially since it was my first result, and also I obtained the data on my birthday, because my birthday is on December 23rd, so that was a nice birthday present as well. And here I zoom out, and I do this just to show you that sometimes this Roster-McLaughlin effect can be very large. So in fact, the velocity anomaly due to the transiting planet is larger than the Doppler wobble of the star from the planet orbiting it. So the full Doppler reflux amplitude is about 200 meters per second. The velocity anomaly from this is 230 meters per second. Now I measured, so I said it's in a nearly polar orbit, so it's the actual measured angle is negative 106. And the reason why this is so large, because I mentioned the size of the effect is based on how fast the star is rotating. So here's the V sin I. It's fairly fast rotator. But look at the radius of the planet, 1.7 Jupiter radii. So it's a very bloated planet, because the mass is less than Jupiter. A colleague of mine at Ohio State, Marshall Johnson, does Doppler tomography work. And because my error bars were kind of large on the spin-orbit angle, he used his technique with the 1D spectra that we had of the star, and also was able to measure the spin-orbit angle. And unfortunately, I chose red. It's right here. So he measured an angle of negative 99.1 plus 4.1 minus 3.9, which is a lot smaller than plus 19 degrees and minus 13 degrees. Anything else? Okay, yeah, that's good. All right. So his result sort of shows the power of using Doppler tomography for fast rotating stars. And of course, I've obtained other results. So I mentioned Hat South, and the reason for that is I was also doing Roster-McLaughlin observations for some of their planets. And here's Hat South 3b. And we observed actually 2 transit events, just because during the first transit, the seeing conditions were kind of poor, and the error bars, or the uncertainty for the spin-orbit angle measurement were pretty large. So we decided to do another transit observation just 7 days later, and the error bars are a little bit smaller. So we were able to determine that it is in an aligned orbit, and then zoomed out. This time the velocity anomaly is a lot smaller than the amplitude from the Doppler reflux. Now, the other interesting thing about Hat South 3 is we also obtained simultaneous transit observations on the August 27th transit using the Folks Telescope South. And the purpose for doing this is to better constrain the transit mid-time, or in this case, the transit ingress time, because often the case, a transiting planet is discovered and then it's followed up maybe years later. So you don't have the mid-transit times are often not very well constrained. So it's good to do transit observations because you can constrain that parameter better with transit observations instead of trying to do that with Roster-McLaughlin observations. Okay, moving along, here's WASP 66. Not a great result, but determined that it is in aligned orbit. Here's WASP 87b, also aligned. Another one, WASP 103. And then this one, I had to change the slide just because I realized that I'll be recorded. And this is a result that I recently submitted and is under review. So these are, again, 3 more transiting planets. But what's interesting is, at least in the case of this one right here, it definitely appears to be on a polar orbit. So this appears to be another planet that's highly misaligned. This one, I'm not as convinced. I did a model fit, and it says that it's misaligned, but you can see that there's a large amount of radial velocity scatter. So I'm hoping that this can be improved using Doppler tomography with my collaborator at Ohio State. Now there's one more result that I want to mention, and so far all the results that I've shown are hot Jupiters. And this is the most sampled parameter space, but one parameter space that's not well sampled is the multiplanets. And I'll mention why measuring spin-orbit angles of multiplanets are important. But here's the result for Kepler-9, and there's 2 planets, or actually 3 planets in the system, but 2 that are important because they're massive, fairly massive planets. So in this case, another aligned orbit, and this is work that I'm doing with a collaborator at Yale University. So we obtained these radial velocities using HiRes on Keck, and we got a pretty nice result consistent with a planet on an aligned orbit. Now, what's interesting about this system is, well, it's multi-planet, but the planets are in resonance with each other. I think it's a 2-to-1 resonance. And because of that, there's significant transit timing variations. In fact, for planet C, the transit timing variations are on the scale or on the order of about 1.5 days. So if you want to observe the transit of either Kepler-9b or Kepler-9c, you better have a good idea of when the transits are going to occur. So we did another transit observation back in September, about 1.5 years ago, to basically update the ephemeris of the transits. And we also did, or my colleague at Yale did dynamical modeling as well to basically predict in the future when we can observe the transit with HiRes. All right, so now I've talked about the results that I've obtained. Now I'll put the results I've obtained and also others have obtained sort of in context with planet formation and migration. So one thing to point out, most of the measurements today are hot Jupiters. And the reason for that is, well, hot Jupiters are more likely to transit, they're larger, so they produce larger amplitude signals, which are easier to measure. And that's what this sort of figure shows right here. So planet mass, orbital period. Most of the ones with spin orbit angles are on less than 10-day orbital periods and of Jupiter mass. Now the ones that I've sort of highlighted here, those are the multi-planets. So there's the hot Jupiters. There's a few warm Jupiters, and those we would also like to sample because we believe that warm Jupiters are planets that are in the process of becoming hot Jupiters and being tidally circularized, because a lot of warm Jupiters have high eccentricity values. And yeah, so one thing that you can do with all the spin orbit measurements that have been collected to date is to look for trends in the data. So one trend that was noted early on by Wynn et al. Is this trend in relation to the effective stellar temperature of the star and the degree of misalignment. Now, when you look at this figure, you'll probably go, well, there's not really much of a trend, temperature versus spin orbit angle. I see quite a few highly misaligned planets around cool stars, as well as hot stars. So one possibility is that the planets might be transiting kind of far away or on long period orbits. Oh, and I forgot to mention this. So why was it originally proposed that cool stars should have planets on more aligned orbits, whereas hot stars should have planets on more misaligned orbits? That has to do with the change in the outer envelope of the star with regard to temperature. So for cooler stars, it's believed that they have convective envelopes, and these convective envelopes can, in theory, realign planetary orbits, whereas hot stars that are above this temperature, and this is kind of the uncertainty here, cannot effectively realign obliquities because they have, instead of convective, they have radiative envelopes. Now I've colored these points here based on basically their distance from the star. So the semi-major axis over the radius of the star. And if I do a arbitrary cut, so if I remove planets where this ratio is greater than 10, all of a sudden the planets that were highly misaligned around cool stars have essentially disappeared, and you do sort of see a trend towards more misaligned planets around hot stars, or at least a more isotropic distribution. And this plot's not that great, but it shows the overall distributions of spin orbit angles that we have measured to date. And you can see most planets are on aligned orbits, as one would expect, but you do see a significant number that are on sort of highly misaligned and even retrograde. So it's kind of see a long tail here. So now, how might you misalign a planetary orbit? So one of the more popular mechanisms is through dynamical means, by driving up high eccentricities. And the most popular is the Lidov-Kozai resonances. So basically, if you have a stellar companion or even a planet that's in a fairly distant orbit and its orbit is misaligned relative to the inner orbit of the planet, or the inner planet, then, and it's misaligned above this critical angle here, which is about 40 degrees, you can generate what's called Kozai cycles or resonances, where the inner planet will increase in inclination. So this plot even though it's cut off. So I believe this one shows the eccentricity of the planet. This shows the orbital inclination of the planet. And basically you have cycles between where the eccentricity of the planet gets driven up to high values and the inclination gets driven to low values, and then vice versa. So they sort of cycle between each other. But this can only happen if the companion to the system is misaligned with compared to the inner planet by greater than about 40 degrees. But this is actually possible, especially in the case of stellar companions, because you don't the stellar companion is not necessarily aligned to the rotation of the primary star. So there's definitely, this is definitely one possibility. And one of the predictions that this model makes is that there is a 3-day pileup of planets through this migration mechanism. And if you look at, again, the figure's cut off here, but here's the orbital period and then just the frequency, you do sort of see kind of a pile up around 3 days of planets. So that shows that this migration mechanism might possibly explain hot Jupiters, but can it explain the high obliquity planets? Does it show the same distribution that I showed earlier for the spin-orbit angles? So there's been some modeling done in regards to kind of predicting the distribution of obliquities for planets. So this is the case for, this modeling was done for G-dwarfs with different planet masses, and then seeing what's the overall distribution of spin-orbit misalignments. And here's for F-stars. But when you compare it to the actual distribution, it doesn't really match up that well. So the Kozai effect, in theory, could produce hot Jupiters that are misaligned, but it doesn't show sort of the same distribution that we see. So there's probably other things going on. And one of the other mechanisms is planet-to-planet scattering. So in order for this mechanism to work, you need to have 3 planets that start to gravitationally interact with each other. And that can drive basically one planet into a very eccentric orbit. And then eventually that orbit, if the eccentricity goes up to a high enough level, near unity, the planet will pass very close to its host star and raise tides on the star, which can circularize the orbit and create a hot Jupiter. But it's kind of hard to see how you can produce a whole lot of... it can account for some high obliquity hot Jupiters, but it's kind of hard to see how you can create a planet on a retrograde orbit. Now the other mechanism, and this is really, does not look good on the screen here, is what's called secular chaos. And how this works is, again, you have 3 planets that are basically sort of on resonant orbits, or have resonances with each other, but the resonances actually overlap with one another. So for instance, the inner planet will have resonance with the next planet out, and also the most distant planets. And these overlapping resonances cause the planet's orbit to become sort of unstable. So that's what this figure is showing, which is unfortunately is not showing up very well. But this is basically showing the periostron and apoostron of the planet's orbit. So when they're widely separated, that means the eccentricity is being driven to very high values. And then right at the end, it predicts that basically the perturbations become so large that the eccentricity gets driven to close to 1. And that results in the periostron of around 3 days, or well, it passes very close to the star, which then eventually, because of tides that it raises on the star, it will start to circularize the planet's orbit, which is happening right here. And you're left with a hot Jupiter. You can also drive up the orbital inclination for the inner planet to very high values. So this is another mechanism that could potentially explain both hot Jupiters and high obliquity planets. And here's the simulated results of the distribution for planetary or for spin orbit misalignments, and it actually appears to match the results fairly well. So this is what's observed, and this is what is simulated. It's not a perfect match, but it's better than some of the other mechanisms for trying to explain these hot Jupiters on highly misaligned orbits. However, it really can't explain planets that are on retrograde orbits. So here's, like I showed here, there's the distribution. And then the last one I want to talk about, the last mechanism, is it's actually possible to potentially create a hot Jupiter through disk migration, like I talked about, and also have its orbit misaligned if you can somehow misalign the disk from which the planet is forming from. So if you do have, so as we know that most stars are not single, they come in binaries or triplets, etc. And those companions can actually potentially could cause the disk to become misaligned with the primary star's rotation axis. So if that's the case, you could form a planet far out and have it migrate in through the disk, and if the disk is misaligned, the planet could end up on a short period orbit that's misaligned, all explained through disk migration. Now, of course, this will need to be tested. So one way of testing this is to see is it possible for protoplanetary disks to be misaligned. You would think that they would be aligned, but if you have a stellar companion, it could potentially misalign the disk. So, again, this is kind of off. So here are the different theories, or the different migration different mechanisms for forming planets and migrating them, and then seeing if and this is the evidence or observations that we have, and seeing if these different mechanisms match the observation. So I'm not going to go through all of them, but none of them explain all of the different observations that we see. So for instance, the spin orbit distribution. secular chaos sort of matches, but not perfectly. I did put a check mark there. Massive outer planet companion. Oh, so if we have observations of massive planets in distant orbits or stellar companions, well, obviously that would match, planet-to-planet Kozai, or planet-to-star Kozai in the case of if we see a stellar companion. And then the 3-day pileup, the Kozai mechanism predicts that. The planet-to-planet Kozai also predicts that. But it's kind of hard to see a 3-day pileup for in situ formation. Okay, so now that I'm running out of time, I will quickly go over some future work that needs to be done to actually determine the origin of spin-orbit misalignments. So one area that we could work on is basically filling up the parameter space that's poorly sampled for these spin-orbit angles. And one place to start is multi-planet systems. And the reason why multi-planet systems are important is because the planets in multi-planet systems typically are believed to have migrated together inside the disk. So you can't have multiple transiting planets if they migrated through one of the high eccentricity or dynamical migration models. So if you find that if all of the multi-planet systems are all aligned, then that suggests that the process that forms hot Jupiters and their spin-orbit misalignments is different from multi-planet systems. If you find that the multi-planet systems are misaligned, then that could indicate that the planets are migrating through the disk, and the disk itself is misaligned. So we do have, so I just mentioned that we have some planned observations of multi-planet systems. So hopefully we can expand this sample, and if we do, if we find that after let's say six measuring the spin-orbit angles of 6 multi-planet systems, and they are all aligned, we can say to about 2.1 sigma confidence that the multi-planet systems are a different population of the migration mechanism is different than the hot Jupiter sample. Because if you were to draw 6 systems from the hot Jupiter sample, the probability that all of them are aligned is very low. And hopefully tests will help us with this. So also warm Jupiters, because these are planets that are in the process of, still in the process of migration, and it's unlikely that their spin-orbit angles have been realigned by tidal effects on the star. So that's another important parameter space. And so again, we need more measurements of obliquities, especially of other types of planets that are not well sampled. We can test some of the migration mechanisms, for instance, the stellar Kozai using adaptive optics. We can test planetary Kozai mechanism doing long radial velocity monitoring of stars to search for additional planetary companions. And then I think at this point, now that we have a large assembly of systems, we can start doing robust statistical analysis to see if there's any more correlations in the data for the various stellar and planetary parameters, and then also actually measure the alignment for protoplanetary disks, or whether they can actually be misaligned with the proto-star, and again, tests. So I will leave it here for questions.
It's messier than I thought. That was my conclusion.
Yes.
Jeremy.
So it seems to me that these mechanisms aren't mutually exclusive. Do you know
No.
if any work has been done trying to sort of simulate what distribution? So like you have 15% of these are caused by Kozai, 10% by some other mechanism.
I think there's been some early work into that. But the problem is we didn't have a large enough samples to do the comparison. But now we're starting to get to that point where we can do some robust analysis in that regard. Yep.
So, depending on who you ask, there's between 13 and 20 circle-binary systems out there. So is there any, like, ideas or plans to look at those specifically? Because I feel like that would be really useful, because you got a planet going around a binary.
Yeah.
Because, I mean, only a few of them are Kepler, if I recall correctly. So there aren't any.
Yeah. If they're from Kepler, then they're probably really faint. So to get high precision radio velocities is going to be quite tough. But if there are some that are bright enough, then you could do the RM effect of both the, if the two stars are eclipsing, then you could get the RM of that and also the RM of the planet transiting either companion or either star. Yeah.
I'm a physicist, and I'm rather wedded to the idea of the conservation of angular momentum. And I wonder, roughly speaking, how much angular momentum is there in the rotation of the star versus the disk or the planet around it?
The planet generally has more angular momentum than the rotation of the star.
That's true in our solar system.
Yep.
The giant planets have way more angular momentum than the sun.
So the angular momentum of the proto-disk that formed everything is more in the...
It's more angular momentum, yeah.
So from an angular momentum point of view, they would perturb the star rather than the other way around.
Well, the transfer's already happened. Right?
Yeah.
So
See, it bothers me that angular momentum doesn't seem to be conserved. You have to have a visitor from elsewhere in order to do that.
I don't think that's a problem. No, the angular momentum is conserved. It's just that it's moved to different locations
Yeah.
in the solar system rather than the central wall.
And that's what's happening when you have migration through the disk.
You get
You're moving the angular momentum from the inner part to the outer part. And you're clear.